So yeah, chapter 7 and 8. Okay, so chapter 7 and 8, it's it's about line integrals. Let me just remind you. So line integrals. We have conservative vector field, vector fields. We have surface integrals. Surface integrals. We have what else? Let me see. Of course, area of a surface. Area of a surface. Area of a surface. And then, yeah, we have of course the Green's theorem. Green's theorem. So now I'm going to include Stokes' theorem in the test because it's in the homework number 6, like the last problem in homework number 6. It's about the Stokes' theorem. So I'm going to finish the Stokes theorem today. But then Gauss divergence theorem, I'm probably gonna cover it today, but it won't be included in the second test because well, you're gonna have another homework, guys, this week, homework number 7. And it's gonna be like due like next week, but it's gonna be due like after the test, right? So what I'm gonna do, I'm gonna include actually Stokes' theorem in the second test. Stokes' theorem, okay, but not Gauss divergence theorem, okay. So we're going to cover Gauss divergence theorem today, but it's not included in the test, okay? Gauss theorem. All right. So everything, I would say, like everything in homeworks number 4, 5, 6 are so they're included in the test. Okay. So I would say I'm going to post, of course, a review sheet today, but I would say homeworks. So homeworks number 4, 5, 6. Okay, so all the problems in homeworks 4, 5, 6 are in the test. I mean, they can be part of the test. Okay, so it's in the test. That's number 2. Okay. Gauss theorem is going to be in the final, of course. The final, of course, is going to cover all the chapters. All right. Yeah, but for the test number 2, Gauss theorem is not. It's not included in the second test. All right. And actually, we're going to have a review on this Thursday. I'm going to do probably like 1 hour, 1 hour and a half, like a review. Okay, and I'm gonna do like 1 hour of new material. I'm gonna probably talk about a little bit about differential forms and curvature of surfaces, but I'm not sure how much time I'm gonna need for that, but we'll see. Okay, so on Thursday, this Thursday, Thursday. So we're gonna have a review for the test number 2. So if you have questions, guys, about the homeworks 4, 5, or 6, or about the review sheet, okay, you can ask me those questions on Thursday. And so we're gonna have a review. I'm gonna try to answer all your questions. But if you don't have any question, I'm gonna cover probably some new material. So I'm gonna cover probably last section, which is differential forms. So last section, differential forms. 8.20. All right, that's the last section in the syllabus. It's kind of short section, so it's not. I don't think it would take a lot of time, but we'll see. Is there any other question, guys? And the final, of course. So the final, it's on May 25th. Final, it's May 25th. and it's at 9 a.m. guys. Okay, so it's from 9 a.m. to 12 p.m. All right, so again, just be careful. The final is going to start at 9 a.m., not at 10. Okay, so the final is going to be a combination of the first and the second test, and also Gauss theorem. So this is final. I would say final. That would be some problems from the first test, problems from the second test, plus Gauss theorem. But anyway, we're gonna have a review for the final next after the second test. So after next week. So it's a Thursday. So the review for the final. So it's gonna be Thursday next week, and that will be May 13th, I think. All right. Any questions, guys? So that's the plan for the coming 2 weeks. All right. So if there's no question, then first, do you have any question about the homework number 6? So homework number 6 is due this Thursday, right? I don't know if you guys have any question. I mean, it's time to ask your question if you have any.
Yes, I'm having trouble with number
Yes.
9, problem 9.
Problem 9. All right. Let's see. Problem 9. Okay, so this is problem 9. Homework. So this is homework number 6. So you need to find the flux of this vector field across the portion of the surface lying over the unit square. So do you have a trouble with which part of the problem? I mean, so first, what will be the flux of this vector field F? So the flux of F, this is, we said this is by definition, this is just the vector surface integral of F along the surface S. Okay, that's what we mean by the flux of F. So that's the integral, the integral of this vector field F. So I would say there are probably 2 steps to do this problem. So the first step, you need to, step 1, you need to parameterize. So first, I would say you need to parameterize S, surface S, parameterize S. Okay, the surface S. What's the surface S? The surface S is given by the graph. So Z is equal to Y e to the X, right? So, I mean, you can imagine you have, you have your 3 axes, X, Y, Z. Okay. And you have this function, Z equals to Y e to the X, right? So you have this Z, which is F of XY, which is Y e to the X, right? So you can imagine, like, so what we do is we graph, so you can graph this function F. And when you graph this function F, so it's like, you have a point in the XY plane. For example, let's say you have a point, I'm gonna take a random point. Let's say you have the point 0, 1. Okay. So what will be F of 0, 1, for example? F of 0, 1 is just like 1 times e to the 0, that will be equal to 1, right? So here's the image of 0, 1, for example. Okay. So what you do is you take for each point in the XY plane, you associate its image, right? So you can imagine, so to each point in the XY plane, you associate its image, and so you obtain like sort of a twisted plane, and that will be your surface. So you obtain like, so this set of the images, so you have this is the set of the images, right? And that will be your surface S, okay? And now you're interested in the portion of this surface lying over the unit square 0, 1, 0 cross 0, 1. So 0, 1 cross 0, 1 would be this. Let's say here's 0, 1 cross 0, 1, right? This is, let's say, 1 here. So 1, and here's my square 0, 1 cross 0, 1, right? So you can imagine, so this is your square 0, 1 cross 0, 1, and to each point of the square, you're going to associate its image, right? So you're going to obtain, like, let's say, this portion of the surface S. That will be that's the portion of the surface lying over the unit square 0, 1 cross 0, 1, right? So does this make sense to you? I mean, I guess you can imagine, like, you have this portion of your graph, so that's your surface, and then all right, so you have to parameterize S. But in general, we said whenever you have like the graph of a function, when you have z equal to something, I don't know, z equals something in terms of x and y. I don't know, let's say x squared y plus sine xy or something, right? So this is a function of x and y, right? So this z is equal to f of xy. So this is a graph of some function f. Okay, so this is the graph of f. So your surface is going to be the graph of f. Graph of xy, right? And so whenever you have a graph of some function, so if your surface is given by a graph of some function, you can always parameterize your S. The simplest way to parameterize S would be to say, well, phi, so S is parameterized by, so we're going to use U and V to parameterize our surface S, right? So the only, you see the only relation between x, y, and z is this one here. So we are saying is that z is equal to y e to the x. So there are no conditions on x and y. So like x and y, they're sort of like independent variables. So I'm going to say like my x is u, so some independent variable. My y is v, that's another independent variable. Right? This is my x, this is my y. And then my z has to be equal to this y e to the x. That's because my surface is the graph of this function f, right? So my z is this f of xy. So that will be f of, because x is u, y is v, that's f of uv, right? So this is just u, v, but then the condition on z is that z is equal to v e to the u. So does it make sense to you, Enrique, why this would be the parameterization of my surface? You see, because the only condition here, I mean, this surface S is defined by this equation, which is z equal to y e to the x, right? That's the only condition you have on these variables, right? That's the relation between, that's the only relation you have on between these variables, right? So when you parameterize, your x is independent variable, y is independent, and you can then you have this restriction on z. Z must be equal to this function of x and y.
Okay, yeah.
Does this make sense to you?
Yeah, I got it now. Thank you.
Okay. All right. So, okay, once you have this parameterization, now the thing is, it's lying over the unit square 0, 1 cross 0, 1. So, I mean, when you say cross 0, 1 cross 0, 1, it means like x is between, it means like x is between 0 and 1 and y between 0 and 1, right? That's like here, like in my graph here, in this picture here. So this is my square. So x is supposed the variable x between 0 and 1 and y between 0 and 1. But then x, that's u. So u is between 0 and 1, v is between 0 and 1. Okay, because v is equal to y, right? U is x and v is y. So this is my parameterization of my surface S with this, and this is the domain. So this is the domain. All right. Now, once you are done with the parameter, so this is like the first step. I mean, that's the we are done with the first step. That's the parameterization of my surface. Now you can compute your flux. So the second step, step number 2, would be to evaluate your. So what's the formula for this flux? I mean, so we said this is F here, right? So it should be like in this way. So you have the vector field F. It's the vector field F along your surface. So this is F of phi of UV. Okay. So which means like your F is, I don't know, what's F here? It's like, you know, F is like Y cubed Z, etc. Right? I don't know. Then what we are saying is that along the surface S, because we are integrating over this surface S, then the X must be equal to U, Y must be equal to V, and Z must be equal to this V e to the U, right? So then here, the Y must be equal to V. So this would be like V cubed, and Z is this thing here, V, you know, V e to the U, right? Etc. etc. So you replace X, Y, Z in terms of, you know, U, V, U and V, right? So that's what we do here. This is your vector field. Now, this is the scalar product. Scalar product with TU cross TV. Okay, DU DV. Now, what's capital TU capital TV? That's the TU is that it's the derivative of phi with respect to U. This is supposed to be derivative of phi with respect to U. Okay, like in this case, like derivative of U with respect to U would be 1. There's derivative of V with respect to U is just 0 because there's no U, right? Etc. And you do the same here. This T index V, that's a derivative of phi with respect to V. So that would be like here U. So derivative of U with respect to V would be 0. This is 1, and here it's just etc. Right? And then you have to do this is the cross. This is a cross product. Okay, so you do the cross product of these two vectors, and you get this vector here. Okay, so you do the cross product of these two vectors, and then you take the scalar product with this vector field F along the surface S. And then there's this du dv. We said u is between 0 and 1, so you're gonna have like the bounds here would be like 0 and 1, and same for v. V is like between 0 and 1. Right? Does this answer your question? I'm not sure which part is kind of mysterious for you, but do you see how it works, Enrique?
Yeah, I see. And
I mean, otherwise, I can also refer you. I mean, we did, I think, a couple of examples, like this problem 9 and like previous lectures. I mean, I can refer you to the, you know, to the recording where you can find, I mean, very, very similar examples. I mean, right? I mean, if he has still trouble with this problem, just let me know. I mean, I can send you like, I can refer you to the recording where we have like a very, very similar problems.
okay. Yeah, thank you.
Any other questions, guys? I don't know, Anis or David, if you have a question, guys. Enrique, is there any question? All right. Anyway, it's I know this homework number 6 is like 10 problems. It's a lot, but it's very. I mean, it's a good practice for you guys. I mean, it's I think it covers like a lot of things. I mean, again, it's a good practice. It's a long homework, but still, I guess it's a good idea to do a lot of problems so you guys can practice. All right. So if there are no more questions, then let's move to the Stokes theorem. So I'm gonna finish the Stokes theorem. I think last week I started like an example, the Stokes theorem, but I didn't finish the second part of the example. But let me just remind you quickly. So what's the idea behind the Stokes theorem? So again, it's like it's a generalization of this Green's theorem. So it relates like a surface integral of the curl of the vector field over a surface to a vector line integral along the boundary of the surface, right? So just to remind you the idea here, the Stokes theorem. So what you have to keep in mind, guys, after the end of the semester, if someone asks what's the Stokes theorem, well, you can say it's just it gives you a relation between because we learn different kind of integrals, right? We have line integrals, that's an integral along paths. We have surface integrals, that's like an integral over a surface, right? So Stokes gives you like a relation between these two different dimensional, like the line integrals is like a one-dimensional integral. Surface integrals are like two-dimensional integral, right? And so Stokes theorem is gives you like a relation between these two different dimensional integrals, right? So Stokes theorem, as I said, so it relates surface integral. So the surface integral surface integral, that's a two-dimensional integral, right? Two-dimensional of the curl of a vector field F over a surface to a line integral. A line integral, that's an integral along a curve or path. So that's one-dimensional integral. Oops, one-dimensional integral of the vector field F, of course, of F, come on, of F along the boundary of the surface. So the boundary of the surface is going to be, of course, a curve, boundary of the surface. Okay. Anyway, so let me just remind you the statement of the theorem. Here's the statement. Stokes theorem. So what does Stokes theorem say exactly? So you have this surface S, some bounded, smooth, nice surface in the space. So let S be, a bounded. Bounded means in some sense you have like a boundary, right? So the surface S has a boundary, bounded, smooth. We know what we mean by smooth. We mean that the normal vector TU cross TV is not zero, right? Oriented, it has orientation. So we discussed a lot the orientation of surfaces, and we said, a surface has two possible, if a surface is orientable, then it has two possible orientations, right? So surface in R3, right? And now we suppose that the boundary of so this is the boundary of the surface S consists of, so we need the boundary to be finitely many simple closed curves. Simple. So remind you, simple means it doesn't have like a self-intersection, except of course at the point where you close the curve, right? Many simple closed oriented curves. So we need to orient the curves, and so we said last time, so the curves here oriented So the orientation of these curves must be consistent with the orientation of the surface S, right? So I explained last week how we need to orient these curves. So oriented constantly with the orientation of S. The orientation of S. And so now if you take a vector field F, the vector field, of course, the domain includes S then. So as I said, so so we have this the surface integral of the curl of F is equal to the vector line integral of F along the boundary of S. Okay, so that's our Stokes theorem. So as I said, the left side, it's a two-dimensional integral, right? It's an integral over a surface. It's the integral of the curl of this vector field F. And the right side, that's a one-dimensional integral because it's an integral along the boundary of S. So the boundary of S would be a curve, and the curve, it's a one-dimensional space, right? So we had an example. I started an example last week. As I said, I didn't finish. So the example. So here's an example. So this is similar to the problem 10 in the homework 6. Okay, so we have to verify. So we need to verify Stokes theorem. So what do I mean by verify Stokes theorem? I have to evaluate both sides of the formula here, right? And we need to check if they are equal or not. Okay, so by the theorem, of course, they need to be equal. So we need to first step. So step 1. So we need to evaluate the left side. Okay. This double integral of this is the surface integral of the curve of F. Right? And then in the second step, we need to evaluate the right side. That's the vector line integral of F along the boundary of S. Okay, and so these two integrals, they must be equal by Stokes theorem, right? So that's what I mean by verify Stokes theorem. So again, guys, like I think in homework 5, probably in homework 5, you had to verify Green's theorem, but I think some of you guys just computed like one side of the formula. Okay, so but when you verify a theorem, you have to we verify a formula. You have to compare both sides of the formula, right? So we have to evaluate both sides and make sure that they are equal. Right. So the left side, I think. So the step 1, I think we are done with the first step. But let me just remind you quickly how we can evaluate this surface integral. So step 1 here. So this was done in last week, but I'm going to just remind you again. Last week. Okay, but so what's the example here? So we have this surface S. So S. So this is surface S is it's a paraboloid. All right, Z equals to 9 minus X squared minus Y squared with the Z positive or 0. Okay. And we need to orient S with upward pointing normal. Right. So I'm gonna first like just graph this surface S so you can see what I'm talking about here. So the thing is, so we have this as a X, Y, and Z axis, right? So if you graph this, so this is Z 9 minus X squared minus Y squared. So you can graph. So f of x, y, it's 9 minus x squared minus y squared, right? So we have this paraboloid. So the vertex of this paraboloid, so the highest point would be 9 actually. So there's 9 here, 9 here, and then here's your paraboloid, right? It's, well, this paraboloid, of course, opens down because of this, minus x squared minus y squared. So you have this paraboloid. Okay. So that's my surface S. Okay. That's my surface S. The Z, of course, must be positive or 0. So that's the portion which lies over the XY plane. Okay. So at the level of the XY plane, when Z is 0, okay, you have this circle x squared plus y squared equals to 9, right? If the Z here is 0, so when Z is 0, we have the circle. So x squared plus y squared equals to 9. All right, so that's my surface S. So we need to orient the surface S with the upward pointing normal, which means that, so as I said, so like here, in this case of this surface S, there are two possible orientations. Either you can orient the surface S with upward, upward pointing normal, okay? Or it could be, your orientation could be a downward pointing normal, right? So it could be like in the opposite direction. And that will be the other possible orientation for this surface S, okay? But in this case, we need to orient S with this upward pointing normal. So it will be this in this direction, okay? So that's the orientation of my surface S. All right, so we need to evaluate this, double. So this double integral over this surface S of the curl. So first step, I would say, so first you need to parameterize. So step 1. So we need to parameterize S. So here in this case, again, S is given by the graph of this function Z equals to 9 minus x squared minus y squared. So the simplest way to parameterize S is to, as I said earlier, when I tried to answer a Ricky question. So the simplest case, whenever you have a graph of a function, you can just say X is U, Y is V, and then Z is your function. So it's 9 minus, so X is U. So it's 9 minus U squared minus V squared. Right now, what will be the domain? Well, remember we said the Z is positive, right? So this 9 minus X minus Y squared must be positive. So in other words, X squared plus Y squared is less than 9. And if you use U and V, that will be U squared plus V squared less or equal to 9. Okay, so the domain here, so the domain, so U squared plus V squared less or equal to 9. That's the domain. All right. So that's the parameterization of S. And then you need to compute. So step 2, I would say you need to evaluate or compute the normal vector. TU cross TV, and make sure that the direction, its direction, coincide with the one required in the problem. Is the one required by the problem. Okay, so like here in this case, TU cross TV, as I said, TU is just derivative of this phi with respect to u, right? I mean, it's just a 1, 0 minus 2u. Okay, we did this on last week. Okay, and then derivative with respect to v, this is just a 0. Sorry, 1 minus 2v, and then if you take tu cross tv, that's 2u 2v1, and then you need to take a point and make sure that you have the right orientation here. So that would be, for example, you can take, for example, remember u and v, u squared plus v squared is less or equal to 9. So we can take, for example, the point where u is 0 and v is 0. That would be the origin, right? So for example, so at the point phi of 0, 0, so that would be phi of 0, 0 would be 0, 0, 9. So this is actually the top of the paraboloid, right? That's the vertex of the paraboloid. All right. In that case, this normal vector. So at that point, so u is 0, v is 0. So in that case, that would be the vector 0, 0, 1. Okay. Right, because you see here u is 0 and this v is 0, so that would be 0, 0, 1. That would be the vector 0, 0, 1. And the vector 0, 0, 0, 1 at the point 0, 0, 9. So again, here's my point 0, 0, 9, right? This one here, this is point 0, 0, 9. That's my point. And the vector, the normal vector at that point would be the vector 0, 0, 1. So that would be this upward pointing vector, right? And that's exactly the orientation required in this problem. Okay, so this is my 0, 0, 1 normal vector. Okay, so the orientation is okay. So we can use this parameterization. Orientation is okay. Right, and then so then this double integral. Oh yeah, before the double integral, we need to compute, of course. We need to find the curl of f, right? So we have this parameterization. So first, step 1, parameterize the surface. Step 2, compute tu cross tv. That's my normal vector. Step 3, we need to compute the curl of f. Step 3, find or evaluate the curl of f. Okay, curl of f is just nabla cross f. Cross product with f, right? So that's a cross product. So so this would be equal to, so remind you, nabla, this is a partial x, partial y, partial z. And you know what's the vector field f, right? And you do the cross product. And actually we computed this last week and we got -3, -1, and +2. Okay. We know the vector field f, we know the del operator, it's this partial derivatives when we do the cross product. Now we have everything, so now we can evaluate in the last step. Finally, we can compute our double integral. So now we can compute. So this S So your vector field F is this one here. Of course, it's along the surface S. So if you have like X and Y in this curl of F, you have to replace X by, the X, Y, and Z. So then you have to replace X, Y, and Z in terms of U and V, right? But here it's just a constant, so we don't have to replace anything. So it's just -3, -1, and 2. And then scalar product with TU cross TV, right? 0. So what's TU cross TV? TU cross TV is 2U, 2V, and 1. So it's 2V. Sorry, 2U, 2V, and 1. DU, DV. Right? And then the domain here, remember, U squared plus V squared must be less or equal to 9. Okay. So in other words, this would be a double integral. So it's going to be like minus 6U minus 2V plus 2 du dv u squared plus v squared less or equal to 9. So in this case, it's better to use polar coordinates. So we used last time polar coordinates, use polar coordinates because the domain is the interior of a circle. So we use the polar coordinates. This is equal. And here use polar coordinates. Right. And anyway, so we did all these details last week, and the answer we got was 18 pi. Right. So this is just the first left side of my Stokes theorem, right? Now I have to compute the right side, and I have to compare, of course, the answers. Is there first any question about this this left side, which is the surface integral of the curl of F? All right, there's no question. So then now the other side. So now, we have to evaluate the other side of Stokes' theorem. So we have to evaluate this, the vector line integral of F along the boundary of S. All right. So we have to, so orientation of this boundary, don't forget the orientation of the boundary must be consistent with the orientation of the surface S. Orientation of the surface S. All right. So how does this work? Well, so let me just graph again. This is surface S, so we can see what I'm talking about here. So I'm going to use a blue for example. So this is my surface S, right? Is this paraboloid here? Okay. Now, what will be the boundary of this paraboloid? It's the boundary would be the circle lying on the XY plane, right? This is X here, of course. This is Y. This is the Z. So the boundary in this case would be this circle here. Okay, so that will be the boundary of S. It's closed. It's a circle, so it's closed. It's a simple curve, right? And so this is my surface S, of course, here. All right, so now I need the orientation of this this boundary of this circle must be consistent with the orientation of the surface. So what's the orientation of the surface? The orientation of the surface is upward pointing, right? So here's the orientation of the surface. It must be, upward pointing, right? So how do we orient the boundary now? This is a circle. remember, we need to use this right hand rule, right? So the fingers, they need to curl in the direction of the orientation, right? So remember, guys, I don't know if you see my hand, right? So use your right hand. Okay, so the thumb points along. So your thumb, I don't know if you see my thumb here. I hope so. So your thumb points along your orientation of the surface, right? So it's upward pointing, right? Now, my index finger points along the orientation of the boundary of the curve, right? And so the middle finger points inside the circle. Okay, so you see here when my fingers curl in the direction of the orientation, so the thumb points along the orientation of the surface S, so it's upward pointing, right? And my index finger points along the boundary, the orientation of the boundary, right? So the orientation of the boundary in this case, it must be counterclockwise, right? So in this case, the orientation of the boundary must be in this way, like this, counterclockwise, right? So then you can see, right? So, my thumb pointing along the orientation of S, that's the red vector, right? And then my index finger points along the orientation of the boundary, that's the green vector, right? So you see, so that the fingers curl in the direction of the orientation, right? So if the surface was like oriented like with a downward pointing normal, all right? So if thumb, you're pointed like downward, right? So then the orientation of so my index finger points along the orientation of the boundary, right? So then the orientation of the boundary, or this is circle, must be clockwise in that case, right? Because my thumb here now points downward. But here in this problem, my thumb must point along the, upward pointing, right? So that's why my index finger actually points along this, it's actually counterclockwise. So I hope it makes sense to you guys why this is the required orientation. So this is what I call consistent orientation. Anyway, so what we have to do now, so first step would be to, of course, we need to compute, we have to evaluate this vector line integral along the boundary of S. So we need to parameterize the boundary of S. So boundary of S is just this circle. Okay, so step one would be parameterize the boundary of S, which is this circle. So what's the boundary of S? So it's this circle, so it's x squared plus, so z is 0, right? So it's x squared plus y squared equals to 9, okay? And of course, the z is 0. Okay, so then we can just, so if you want to parameterize this boundary, you can say, well, my x, you can use the polar coordinates, right? Because the x squared plus y squared equals to 9. So you can say, well, x is 3 cosine of t, let's say, y is 3 sine of t, and what will be z? Well, z must be 0 because this boundary, this curve lies on it's lying on the xy plane, so z is 0. All right, so this is my x, this is my y, and this is my z. And of course, I'm using here just one parameter, which is parameter t, because this boundary, it's a path, so it's a one-dimensional space, right? So we use just one parameter. And of course, when you do here, you do x squared plus y squared, that will be equal to 9, and the z is 0. And of course, t would be between, the domain here, t is between 0 and 2 pi. Okay. Now you need to make sure that this is your orientation of this curve is counterclockwise, right? So what you can do, guys, you can just, make sure that you are going in the right direction. So for example, so make sure that it's counterclockwise oriented. Right. So what you can do is just you can take, for example, well, you can say, for example, when t is 0, gamma of 0 would be the point, 3, 0, 0. And when, let's say, t is pi over 2, for example, gamma of pi over 2 would be, well, it would be 0, 3, 0. So you move like, you move like, so 3, 0, 0. Let's say this is, this is a 3, 0, 0. And here, this is my y-axis, so this is 0, 3, 0, right? Etc. etc. Anyway, so we are saying that at time t equals to 0, we are at the point 3, 0, 0, and then at pi over 2, we are at the point 0, 3, 0. So we are moving like from 3, 0, 0 to this 0, 3, 0, etc., etc. And that will be counterclockwise rotation, right? So anyway, so yes, so the parameterization yields the orientation desired for the boundary. So the orientation of gamma, the orientation is consistent. The orientation of gamma is consistent with the orientation of the surface S. All right. Anyway, so now we can just compute this. We know how to compute this vector line integral f ds. So it's f of gamma of t, scalar product with the derivative of gamma prime of t, dt, t between 0 and 2 pi. Right, and we know how to do this, of course. So my x is 3 cosine of t, my y is 3 sine of t, and z is 0. So for example, my f is, my vector field f is, what's f? What was f? F was, was I think 2z minus y, x plus z, 3x minus 2y. Okay, that was my f. So if you do f of gamma t, that will be equal to, so z is 0, z is 0, x is 3 cosine of t, and y is 3 sine of t. That's along the curve gamma of t, right? So that'll be like 2 times 0 minus y, so 2 times 0 minus 3 sine of t, etc., etc., right? Anyway, so this so this line integral would be actually 0 from 0 to pi. So the vector field f would be, I think, minus 3 sine of t, 3 cosine of t, and then 9 cosine of t minus 6 sine of t. Okay, that's my vector field f along the gamma of t. Scalar product with my gamma prime of t. So that would be minus gamma prime, derivative of gamma, derivative of sine, that would be cosine, so cosine of t, derivative of 0, of course, is 0. All right, so this is from 0 to pi, and actually you get, so 9 sine square plus 9 cosine square plus 0 dt, so that'll be 9 dt, and that's exactly 18 pi. Okay, so we get the same answer as in the surface integral. So yeah, so the conclusion is, of course, Stokes' theorem is verified, and so both conclusion. So Stokes theorem is verified. And so both sides, so the curl of F along this surface S is equal to the vector line angle, the line angle of my vector field F along the boundary of S. So both are equal to 18 pi. All right. Is there any question, guys, about this example? I know it's a lot of information here to process, especially with the parameterization. So I think the problem with the in this case would be, make sure that you have the right parameterization. So you have to parameterize your surface or your curve, right? But once you have the parameterization and you make sure that you have the correct orientation, then I think it's just it's kind of straightforward. Okay, let me show you with an example why this Stokes theorem is a very powerful theorem. But so first, let me just remark why the Stokes theorem is a generalization of Green's theorem. So first remarks. So first, so as I said, this Stokes theorem is a generalization of Green's theorem. So in Green's theorem, in Green's theorem, we have this surface S in R2. We have a surface S in R2. Okay. Now, if you see this surface S as a surface in the plane, in the space. Okay, now let's see. So surface S now in the space in R3. In R3 in the space. Okay. Then what will be the normal vector? So then a normal vector to S is actually K, the vector is 0, 0, 1, right? Because so what I'm saying, guys, is that so you have your X, Y plane. So we have some surface S lying in the XY plane in R2. So this is my surface S, right, in R2. Now, if I consider this surface S in R3, then a normal vector, to this surface would be the vector 0, 0, 1, right? So like if you take this vector here, the vector 0, 0, 1, it would be normal. It's a normal vector to this surface S, right? So in this case, the orientation actually of the, remember in the Green's theorem, we need to orient the boundary of the surface so that the surface would be on the left as one traverse the boundary of S, right? So so in this case, in the Green's theorem, we need to orient the surface S, the boundary of the surface S, so that the S would be on the left of the orientation of the boundary, right? So like here in this case, the boundary would be oriented like this here. Okay, so the inside of the interior of the surface S would be on the left of the orientation of the boundary, and so this orientation here is consistent with this normal vector given by 0, 0, 1, right? Because in that case, so the thumb, if you use your right hand, right, the thumb, the thumb actually would points along this normal vector, right? This is vector 0, 0, 1. The index finger points along the orientation of the boundary, right? And then the middle finger points inside the surface S. Anyway, so all I'm saying is that if you take this normal vector 0, 0, 1 to S, then actually we're gonna get a consistent orientation. Okay, so the orientation here is consistent. Consistent with the orientation required in Green's theorem. All right. Anyway, yeah, so I was saying I'm going to show you with an example why this Stokes theorem could be very powerful sometimes. So here's an example. Number 2. So so this Stokes theorem can be very useful sometimes. Very powerful. Okay, so let me show you with an example why this Stokes theorem can be powerful. So here's an example. Okay, example. Well, so let's say you have this vector field F. So F is a very complicated vector field. Let's say it's e to the y plus z minus 2y x e to the y plus z plus y, and then let's see, and then e to the x plus y. Okay, that's my vector field F. And then let's say my surface S is given by the graph of a function. So graph of, so here's my z equal to f of xy, which is, let's say, e to the minus x squared plus y squared. Okay, with z, let's say z is larger than 1 over e. Okay. So when you say z is larger than 1 over e, it means that actually your x squared, plus y squared would be less than 1. Because so in other words, z is supposed to be equal to e minus x squared plus y squared, right? And we are saying that this is less than 1 over e. Okay, so if you apply natural log, so in other words, so the e would be larger than e to the x squared plus y squared, right? Just take the reciprocal here, and you apply natural log. Apply log or natural log to both sides. Natural log of e would be 1. Natural log of e to the x squared plus y squared would be x squared plus y squared. Okay. So anyway, so what I'm saying here is that when you say z is larger than 1 over e, it means that x squared plus y squared is less or equal to 1. Okay. Anyway, so that's my vector field F. That's my surface. So the surface S is a graph of this function with the S with the z larger or equal to 1 over e. So actually, I mean, if you want to graph, you can graph this surface S. So here, so z is larger than 1 over e. So here, this is 1 over e. Of course, if z is equal to 1 over e, if z is equal to 1 over e, then actually x squared plus y squared is equal to 1. So here we're going to have a circle. Okay, this is a circle x squared plus y squared equals to 1. And then, so actually the z, because z is equal to e minus x squared plus y squared, so e to the power is negative, right? The power of e is negative. So the maximum here, I mean, e to a negative power, the maximum would be equal to 1, right? I mean, the graph of the exponential, right, guys? If you have the graph of the exponential, when e is, this is e to the 0 is equal to 1. So this is e to the x. So the maximum, if your power is negative or 0, the maximum would be e to the 0, which is 1, right? So the highest point of this graph would be just equal to 1 here. So this is 1. Okay. And so here's my surface S. This is 1. Okay, this is my surface S. Anyway, so this is my F, this is my S. So if you want to compute, let's say, okay, you want to compute, the left side of Stokes' theorem, the curl of F, over the surface S, right? Let's try to evaluate this. Okay, well, first you need to compute the curl of F. I'm gonna probably just skip the computations here. I mean, you know F, you know how to compute the curl of F. So curl of F actually, if I'm not mistaken, if my computations are correct, curl of F would be like e to the x plus y, minus x, e to the y plus z, e to the y plus z minus e to the x plus y, and 2. All right. Anyway, so that's the curl of F. Now we need to parameterize S, right? So now parameterize S. S is just a graph of some function. So as usual, we can just say, well, phi of u v, x is u, y is v, and then z is given by the function. The function is e to the, e to the minus x squared plus y squared. So that's e to the minus u squared plus v squared. All right. And as I said, x squared plus y squared is less than 1. So this u squared plus v squared is less or equal to 1. Okay. Now, you compute, derivative with respect to u, derivative with respect to v, and then compute tu cross tv. Again, I'm going to just skip the computations. I'm going to give you the answer here. If you do tu cross tv, that will be, I think, 2u e to the minus u squared plus v squared minus 2v e to the minus u squared plus v squared and 1. Okay. And then you have to, so now double integral is going to be very hard to compute because, so we're going to have this curl of F, scalar product with this tu cross tv, du dv. Of course, domain here, again, u squared plus v squared less than 1. But I mean, if you do the scalar product here, it will be very, very, it's going to be very hard to actually evaluate. So this is like 2u e minus I'm doing the scalar product of the curl of f with this normal vector, okay? U squared plus v squared, e to the u plus v minus u, e to the v plus the z. So it's z here, so it should be z here. So z, I mean this whole thing here, okay? That's my z. Anyway, plus like, I think plus 2v, etc., du, dv, okay? Anyway, so all I'm saying, guys, is that you're gonna end up with very hard integral to compute. It's gonna be very, very long and very actually hard to compute. Okay, so this integral is gonna be very hard, even if you use the polar coordinates, because the thing is, well, here it's good. You have u squared plus v squared, but at some places you're gonna have this u plus v, like arc cosine, or so even if you use the polar coordinates, like you're gonna have like e to the r cosine plus r sine. So this is really bad here, all right? Really bad. So anyway, so what I'm saying is that this integral is gonna be very hard to compute. Okay. Okay, now our hope is that the right side of the Stokes theorem would be easier to compute, right? So the right side. Okay, now let's check the right side. So this is, again, the right side would be this vector line integral of f along the boundary of S. Okay. So what's the boundary of S here? Well, again, it's gonna be, the boundary in this case, we're gonna be this circle here, this one here. Right, you're gonna have this circle, that will be the boundary of S. So this is C, boundary of S. So again, it's a circle, it's x squared plus y squared equals to 1, but the z is equal to 1 over 8. So this is x squared plus y squared equals to 1, and z is equal to 1 over 8. Right? This is the boundary of my surface. All right, so how can we parameterize this boundary of this surface? X squared plus y squared equals to 1. So we can say x, this is a curve, right? So it's just a one-dimensional space. So we're going to use just one parameter, which is t. So that would be cosine of t plus, so x cosine of t, y sine of t, right? And the z is 1 over 8. So if you parameterize, so let's parameterize the boundary of S. Okay, so that would be, as I said, this is just x as a circle, x squared plus y squared equals to 1, and then z must be 1 over 8. All right, so gamma of t would be like, cosine of t, sine of t. So then, x squared plus y squared will be 1, and then z must be 1 over 8, because the height, so the circle is at the height z equals to 1 over 8. Right, so this is my, again, x, this is my y, and here's my z. And of course, as I said, do x squared plus y squared will be 1. And so t, of course, it's a circle, so t is between 0 and 2 pi. All right, so anyway, so now if you do, if you try to evaluate this vector line integral, the integral of f along the boundary of S. So again, this is by definition f of gamma of t, scalar product with gamma prime of t, dt, t between 0 and 2 pi. Now, if you do the substitution and you compute the scalar product, etc., then you're going to end up with this. So here I'm jumping some steps here because I assume, guys, that you know how to compute this, this scalar product. So after your steps, there are a couple of steps here, of computations, you're gonna end up with like 2 sine square minus sine of t, e to the sine of t plus 1 over e plus like cosine square of t, e to the sine of t plus 1 over e, etc., etc. But this is also really hard to kind of very hard to evaluate because I mean, it's kind of impossible to integrate this because as you can see, for example, here I have e to the sine of t, and here's the sine of t. It's not even the derivative of sine. I mean, if it was cosine of t here, then yeah, that would be like the derivative of e to the sine of t. But this is sine of t times e to the sine of t, so this is going to be a mess to integrate. And this is also here another mess. Like you have cosine squared of t times e to the sine of t. This is very hard to actually integrate. So yeah, I mean, I can just wish you good luck computing this integral. So this is also hard, very hard to. So this is also very hard to compute. Okay, so the question is, so how can we compute this? So question. So how can we so how can we compute such an integral, right? How can we compute? Such an integral. Okay. Well, the idea is the following, guys. So in some sense, we're going to try to use this Green's theorem. So what we're going to do is the following. So let me just remind you the picture here. So our surface S was this graph. You know, we have this. Right, this was our surface S. All right, this is our surface S, and the boundary of the surface S was this circle. Right. This is, of course, this is here. We have this is 1 over e. Okay, so this is 1 over e here, and here in the top we have 1. So what I'm gonna do, guys, the thing is, these two, so if you consider now a different surface, so I'm gonna take this surface, which is the disk. So I'm gonna take this surface here, this one here. Okay, this disk here. Okay, the bottom. So you see the bottom of the, the bottom of my surface S, this one here, this disk here. So let's call this disk S prime. Okay. So what I'm saying, guys, is that, so let's say S prime. So this S prime, this is the disk, unit disk at z equals to 1 over e. So this is disk. So x squared plus y squared less or equal to 1, right? With z equals to 1 over e. Okay. Now, so the thing is, the surfaces S and S prime, they have the same boundary. So here the remark, I mean the observation here is that S and S prime, both they have the same boundary, right? Both their boundary is, for both of them, the boundary is this circle, x squared plus y squared equal to 1. at the level, at the height, z equals to 1 over e, of course. Okay, so the point here is that, so the observation here is that, so S and S prime have the same boundary, right? They have the same boundary here, which is the circle x squared plus y squared equals to 1 with the z equals to 1 over e. Okay. So the thing is, so if you, I mean, if you want to compute this curl of f along S, right? Along the surface S. So this is, you know, by, of course, by Stokes' theorem, this is supposed to be the integral along the boundary of S, right? F. Okay. But what we are saying is that S and S prime, they have the same boundary. So this integral here will be also, this is actually equal to the integral of F along the boundary of S prime. Okay, because again, S and S prime, they have the same boundary, right? So you're integrating this vector field F along the same thing, along the curve C, which is, but it's the thing is, this curve C is the boundary of two different surfaces. Okay, so that's why here, so they are equal here because, you know, boundary of S is equal to the boundary of S prime. Okay, so your integral is along the same thing here, is along this circle, x squared plus y squared equals to 1 with a z equals to 1 over e, right? But now if you use the Stokes theorem, so this is equal to, if you use the Stokes theorem, so by Stokes theorem, oops, by Stokes theorem, this is a double integral of the curl of f along S prime. Along S prime. Oops. Okay. So here I'm using Stokes theorem, here I'm using Stokes theorem, but here all I'm saying is that I'm integrating along the same curve, which is the boundary of both of S and S prime. All right. So now the thing is, let's see what will be the integral of the curl of f along S prime. Okay. So now let's see. Now let's evaluate this curl of f along S prime. Right. Again, the thing is, so the idea, guys, is this is really hard to compute, right? We said this is hard to compute, right? This is also hard to compute, and this is also equal to the same thing, right? It's just the same thing here. This is the same integral because we have the same same curve, same boundary, so it's just the same integral. But here, this is a different thing. Here we have, so it's equal to this curl of f, but over S prime, not over S. Okay, so let's see what will be the curl of f over S prime. So over S prime is just this circle. Again, this is S prime is this unit disk, x squared plus y squared less or equal to 1. So this is the interior of this circle here, with the z equals to 1 over e. So let's parameterize this S prime. Okay, so parameterize S prime, and let's see what will be the curl of f along S prime. Okay, so so again, this is just x squared plus y squared less or equal to 1, and the z is 1 over 8. So we can just use, polar coordinates. So phi r of theta, phi of r theta, that will be r cosine of theta, r sine of theta, and z is equal to 1 over 8. Okay, so r is between x squared plus y squared less than 1, so r is between 0 and 1, and theta, as usual, between 0 and 2 pi. Okay, so you do tr, you do t theta. Now the normal vector would be, so tr cross t theta, that will be equal to, it's very easy to compute. Actually, the answer here would be 0, 0 r. Okay. I remind you, the curl of f was a very complicated expression, right? It was like e to the x plus y. I don't know, it was minus x, e to the y plus z, etc., etc. But then for the z coordinate, we have 2. Okay, so for the z is just equal to 2. But the x and the y are very the first, the first and the second, the first and the second component. So the last component here is very easy. It's just equal to 2. This is a last, it's not z. This is a last component. Last component of the curl of f is just equal to 2. The first, so the first and the second components are very complicated. Okay. But the thing, guys, you see here in the normal vector of my surface S prime, it's just 0, 0, r. So when you take the scalar product, so the first component times 0 will be 0, plus the second component times 0 will be 0. So it doesn't matter what you have in the first and second component, because you're going to have just 0. And all you have to do is just multiply this r by 2. So when you compute the curl of f, along S prime, okay. So the curl of f, as I said, here is going to be very complicated, but the last component will be just 2. Okay, so this is very complicated here. Okay, scalar product with my normal vector, which is 0, 0, r, the r d theta. R is between 0, 1, theta is between 0 and 2, right? So when you do this scalar product, you end up with just 0, 2 pi, 0, 1. It doesn't matter what you have in the first and the second component of your vector field. They are very complicated, but it doesn't matter. Because when you do the scalar product, you just end up with this 2 times r. So that will be 2r here, just 2r, dr d theta. And this is very easy, of course, to evaluate, right? The answer here would be just equal to 2 pi. Okay. So the conclusion is that remember, guys, we had to evaluate the curl of f along this surface S, but it was very hard to compute, to evaluate, right? But then we said this is equal to, by Stokes theorem, this is just a f, sorry. This is just the vector line integral of f along the boundary of S, which is the C. The circle x squared plus y squared equals to 1. That's the boundary of S. Okay. But this was also hard to evaluate, right? But this is equal, the same thing. But I'm going to use a different surface, so S prime, and S prime has the same boundary as S. So here, this is just the same integral, because this is S prime here. Let's see, this is boundary of, so this is this curve C, boundary of S prime, okay. As I said, this was hard. This is also hard to compute. These two are just the same, okay. But then we have this by Stokes theorem here. Using the Stokes theorem here again. Stokes. So we are saying that this is the double integral of the curl of f over S prime. And S prime is a different surface than S. This is S prime. But this one here turns out to be very easy to evaluate. This one here turns out to be very easy to evaluate, right? It's just equal to 2 pi. It's equal to 2 pi. Okay. So, yeah, so the idea here, guys, so let me just, again, remind you what we did here. So we started with, so we have this vector field F, kind of complicated vector field F, right? We have this surface S, which is this thing here, this graph here, right? But this surface S has this boundary, which is some circle here, right? This circle, okay? And what we tried to evaluate this curl of F over S, right? It turns out to be very hard to compute. And if you use the Stokes theorem, this is supposed to be, you know, the vector line integral along the boundary of S, which is also actually, it turns out also to be hard to evaluate. Okay, so both here are hard to evaluate. Okay, so what we did is we took another surface which has the same boundary as S. So we took this surface here, which is this disk. You see this disk here at the level, so this is supposed to be like level 1 over E. So we took this disk, the interior of this circle, that's my surface S prime. This is a different surface, right? It's different from the blue one, right? But the thing is, S prime and S, they have the same boundary, which means that this thing here, this vector line integral, is just the same, because S and S prime, they have the same boundary. So this is just the same integral, right? It's the same vector field and the same boundary, so it's are equal. And now if you use again Stokes theorem, this is curl of F along S prime. But this one here along S prime turns out to be easy to evaluate. Okay, this one here is easy to evaluate. And that's the power of this Stokes theorem, right? Because if you have some surface integral, so if you have the integral of a curl of a vector field along some surface, and if the integral turns out to be hard to compute, okay, and even on the boundary, it's also hard to compute, all you have to do, guys, is, you know, if you take a different surface with the same boundary, all right? So if they have the same boundary, it means that this vector line integral is going to be the same because it's the same, it's along the same path. Okay, but then you use again this the Stokes theorem, so that would be the double integral over this S prime. So that would be a different integral to evaluate, and sometimes it turns out to be easier than the initial one, right? Right, I don't know if you have questions, guys, about this. So that's the idea here. I mean, this shows like why this Stokes theorem can be very, very useful sometimes, because you start with some integral over some surface, turns out to be hard to compute. All you have to do is to pick a different surface with the same boundary as the initial one, and then you can use this, your Stokes theorem to evaluate your initial integral. All right. Well, we only have 9 minutes to do the Gauss theorem, and that would be impossible, of course. So what I'm gonna do, guys, probably I'm gonna do Gauss theorem on Thursday. Of course, I'm gonna, if you have any questions about the review sheet, I'm gonna try to answer them, but I'm gonna do the Gauss theorem on Thursday. So here's an exercise about Stokes theorem. Well, I'm not sure if we're gonna have time to do the exercise, to go over the exercise today, but so first exercise, so we need to, let's say S, surface S, defined by x squared plus y squared plus 5z equals to 1 with z positive, right? The surface is oriented upward, with upward pointing normal. Okay, and let's say your vector field F is xz, yz, x squared plus y squared. Okay, so what you have to do in this first exercise, guys, is to verify Stokes theorem. Okay, exercise number 2. So in this exercise number 2, you will see, I mean, if you try this exercise, you'll see that it's actually, turns out that your double integral and your line integral are kind of hard to compute. And so the idea would be do the trick I did like in the previous example where I had to change the surface, right? So let's say you have this surface. So as surface defined as given by the graph, so by z equals to 4 minus 4x squared minus y squared, right? With the z positive. Let's square here. With the z positive, right? Oriented by, let's say, oriented by a normal with non-negative, with non-negative k component. So the third component is not negative, with non-negative k component. K component, that's the third component. So the third component is non-negative. All right, and let's say F is, vector field F is x cubed e to the y squared and z e to the x y. Okay, and the question is to find double integral of S, curl of F. So in this second problem, guys, this integral here, if you try to evaluate this integral, is going to be kind of hard to evaluate. It's going to be very complicated integral. Okay, and if you use a Stokes theorem, you're going to have this vector line integral, so the integral along the boundary, and the integral along the boundary is going to be also hard to evaluate. Okay, so the idea here would be to integrate over another surface which has the same boundary as S. So hint here. So we need to integrate over another surface, say S prime, which has the same boundary surface S. Okay, so what I'm saying, guys, is that, so first, if you try to do this, oops. So if you try to evaluate this one here, this one is going to be hard to evaluate, and apply Stokes theorem. This is also going to be hard to compute along the boundary. So this is a C, which is the boundary of S. So this one is going to be hard. This is also hard. I mean, if you use Stokes theorem, still hard to evaluate. Then, but this is, so if you pick now a different surface with the same boundaries, so we're going to have, of course, the same integral here. This is also hard to evaluate because it's the same vector field along the same path. Okay. So these two are the same integral. Okay. But then you can use Stokes theorem to say that this one here is actually the curl of f, but along S prime, and that's a different integral. And this one should be easier to evaluate. So this is over S prime. Okay. So you may ask, well, what will be this surface S prime in this case? Well, I mean, you can try to graph your surface S, like here, like in this exercise number 2. You know, your S is just the graph of, so it's like a Z4 minus 4x squared minus y squared, the Z positive, right? In other words, you know, Z is positive, so 4x squared minus y squared is less or equal to 4, so plus here, to 4, right? So in other words, if you try to graph this surface S, so you're going to have the highest point would be the point 0, 4, 0, 0, 4. So you're going to have something here. Z is positive, so it's something like this here. But here the boundary, it's not, you know, when Z is 0, as you can see, when Z is 0, you're going to have 4x squared plus y squared equals to 4. Okay, so that's not, of course, that's not, you can divide by 4, for example. So this is x squared plus y squared over 4 equals to 1. So this is not exactly a circle, it's an ellipse, right? So the boundary in this case would be an ellipse. You know, this would be like sort of an ellipse here. It's not exactly a circle, right? And so this is your surface S. Anyway, this is my surface S. It's the top of, this is the surface S. Okay. This is your surface S. What's the boundary of this surface? It's just the circle here in the bottom. The circle lying on the XY plane, right? Where Z is 0. Sorry, not the circle, ellipse, I mean, sorry. So X, Y, Z. So in this case, the boundary would be this ellipse here, which is, again, x squared plus y squared over 4 equals to 1. Okay. As I said, if you want to integrate this curl of f along S, is going to be very hard to evaluate. The same of the vector line integral here along this ellipse is going to be also hard to compute. But the idea here is to change, is to take a different surface, S prime, which has the same boundary as S. So what would be the S prime in this case? Well, the simplest choice here for S prime would be this disk, not the disk, but the interior of this ellipse. Okay, so S prime, the simplest choice for S prime here, that will be, you know, x squared plus y squared over 4 less or equal to 1, and of course Z must be 0. Okay, that will be S prime. Anyway, guys, I'm gonna stop here. Of course, I don't have time to go over these exercises, the problems. So on Thursday, as I said, so I'm gonna post the review sheet for the second test later this afternoon. All right. So on the Thursday, so we're gonna have like a sort of review. I'm gonna try to answer your questions. If you have any questions about the homeworks 4, 5, 6, or about the review sheet, I will answer them on Thursday, and then we're gonna go over finish with the Gauss theorem, right? And then next week we're gonna have the test on Tuesday, and on Thursday I'm gonna have like a small review for the final. And if I have time, like for 1 hour, I would talk about the last section, which is differential forms. Okay, guys. Thank you everyone for listening, and I guess I'm gonna stop recording here.